So in order to solve a differential equation, we are going to need a little bit of integration to do that. We're going to be starting with some sort of expression of dy over dx, and we need to be able to find y. So we will need to include some integration or some anti-differentiation strategies to do that. When we integrate, we include a plus c as a part of our work to represent the constant that might be there when we do our anti-differentiation. So as long as we have that plus c in that solution, what we've done is we've are finding a general solution for that equation. When we have additional information, and it's usually some sort of initial condition, like some kind of point that they'll give you, then we'll be able to plug in that point into our general solution to be able to find a specific solution. So in general, we're going to always try to find specific solutions where possible, and we have this five-step process in here to work on this. These 5 steps are really all of the things that you want to be walking through to gain as many points as possible on a free response type of section. Usually, these types of questions where you're solving a differential equation could be worth from 4 to 5, sometimes even 6 points out of the 9 for that particular question. So it really is important to follow all of these steps and to learn this process really well. So we're going to find both a general and a specific solution as examples for today. And we're going to get started as we walk through kind of the very first steps. In our example down here, we're going to find just a general solution for the differential equation that's in there. And the very first thing that I'm going to do is I'm actually going to change the y prime into a dy over dx. The reason we're going to do that is we're going to separate the variables. We are going to move all of the y's onto one side and all of the x's onto the other side. So we are going to separate this derivative in here into a dy and a dx, and the dx is going to move over to the other side, similar to what we did when we had to use u substitution and kind of isolate what dx was in that relationship. We're going to do something similar. We're just going to multiply dx over to the other side. So 3y squared times dy is equal to the quantity of x squared plus 2 times dx. So that is your first step of separating your variables. The next step we're going to do is to anti-differentiate each one of those sides. And it's kind of like an equation where you have to keep things balanced. Whatever you do to one side, you have to do to the other, and that's why we're integrating both sides at the same time. So the antiderivative for 3y squared would turn out dy, because again, that's your integrals ending in dy, so y is your variable over here. We're going to end up with y to the third. And the antiderivative for x squared plus 2 dx would be a 1/3 x to the third plus a 2x. Now, there's normally a plus c with each one of these, but because we have a plus c on one side and a plus c on the other, and we really don't know if those are the same, if they would cancel out or anything like that, we're just going to keep one plus c over on the right, and that's going to represent both constants from both sides. So let's say, we had a constant that was supposed to be 1 on the left-hand side and a constant supposed to be 7 on the right-hand side. We're just going to combine those like terms to make one constant on the right. That would be normally 6 with those numbers I just gave. But we don't really worry so much about what the numbers actually are because we're trying to solve, right? And so we're going to have a specific point that will help us solve for those c's later. So we're going to use our initial condition if it's given. In this case, we don't have an initial condition. We're just solving for the general. So we're going to skip step 3. And then we're going to solve for y. So when I look at this expression, all I have left is that cube that I need to get rid of to isolate the y. So I'm going to go through and take the cube root of the entire other side of this function, x to the third over 3 plus 2x plus c. And that ensures that we have our general solution. Now, I also have here in step 4, replace y with f of x or some other appropriate label. They didn't use any other labels in our example here of a y or an f of x, or this is not coming out of a prompt that has some kind of context to it. So we don't need to replace anything because they're not letting us know to do that. The last part right here is step 5, ensuring the solution works with the initial condition. Since we didn't use an initial condition and this is just your general solution, this is as far as we're going to go. All right, so this is going to be my solution. to the differential equation above. In our next example, we are going to solve using an initial condition. So we have to find the specific solution for dy over dx equals x squared over y if we know the point that y of 3 is equal to negative 2. So we're going to start off by separating our variables. I'm first going to move the y that's in this denominator over to the left-hand side to get y times dy over dx is equal to x squared. And then I'm also going to move the dx over to the right-hand side, similar to the way I did before, to get x squared times dx. Next step, after we've separated our variables, is we're going to integrate both sides. So the antiderivative for y dy is going to be a 1/2 y squared plus a c, but we know we're going to move it to the other side anyway. The antiderivative for x squared will be a 1/3 x to the third, and that's where the plus c will go. Now, this is the point where we do have an initial condition, and I highly recommend that you find what the c value is going to be right here before you go any further. So the point that they're giving is x equals 3 and y is equal to negative 2. So that's what we're going to plug in. 1/2 times a negative 2 squared is equal to 1/3, 3 to the third plus c. So we're looking at a total of 2 is going to be 1/3 of 27, which is 9. And we get negative 7. So now our solution is more looking like a 1/2 y squared is equal to 1/3 x to the third minus 7. So we've used our initial condition. So now we're going to go and actually solve for this y value. So the first thing I'm going to do is multiply everything by 2. So I get y squared is equal to 2/3 x to the third minus 14. And then I'm going to square root that entire expression. And when you square root, we get a plus or minus 2/3 x to the third minus 14, all in that radicand. Now, our last step said that we need to make sure that we have a solution that works with the point that's given. The point that we were given is 3, negative 2. So we need to pick a function out of here that works with the point 3, 2. The problem we have right now is this plus or minus that's in front of here. That's two different functions that we have at our disposal. And we want to pick the function that specifically works with the point 3, negative 2. The other function, maybe it is a really good solution for this differential equation, but it won't contain the point 3, 2. So we want to pick the one that has that point on it. So if we think about this, if we want to end up with a y value that is negative, we're going to need to have the negative sign on the outside of that radical in order to make that work. But we can also double check to see what happens. So for example, negative 2 is equal to the square root of 2/3, 3 to the third minus 14. And again, all of this would end up being a positive 2, but we need the negative sign out here in order to make it turn into the negative 2 that's in our point. So the function we're going to pick is y equals negative square root of 2/3 x to the third minus 14. And that will be our specific solution for this particular problem.